Welcome to the session on journaling SoftUpdates. Let me start by saying a little bit about how this all came about. You'll notice that there's two names on here, mine and Jeff Robertson's. And it actually started out because Jeff came to me actually at the last one of these events and said, you know, you've got this SoftUpdates thing, why don't we just add a journal for the few things that it has trouble with, and that way you don't have to run that BackgroundFSK thing. And our thought at the time was this was going to be like a really simple 1,000-line hack. Well, the beauty of being an old fossil such as yourself is that when you're pushing 60, you find somebody that's more like pushing 30 that can help out on the project. And what this means is that the fossil gets to say, well, why don't you try this or that? And then the other person goes off and actually does all the coding. And then when they do that, you look at it and complain about it. And so in this way, it iterates and it moves forward. And this worked extremely well in this particular scenario. So the fact of the matter is that Jeff's probably the one that should be up here giving this talk, except that he has an allergy to being around large numbers of people for more than a day or two. So he came to the Dev Summit, and for those of you that were at that, you got to hear his talk about it. But he just couldn't fathom actually being around people for 5 days without a break. So I can report, is safely back in Maui with his cat, dog, and wife, and is much happier for it. So I'm going to give the talk today. And unlike the one that he gave at the Dev Summit, where he assumed that you had the intimate knowledge of how SoftUpdates work, I'm going to assume that perhaps you don't. And so, in fact, what I'm going to do is start by introducing SoftUpdates and sort of what's the problem they're trying to solve and how do they go about doing that. Having sort of set that groundwork, then I want to talk about what of the SoftUpdates, or what it is that SoftUpdate doesn't do that we need to journal. And then it turns out there's a few extra requirements that we have to put on the journaling in order to make the whole package work. And so we'll sort of go through there and look at what it is that we're journaling. And then, of course, the interesting part of it is what do you do after a crash? So I'm going to go through the crash recovery phase and show how it is that the journaling essentially fixes all the things that would traditionally be fixed by BackgroundFSK. And then we'll talk a little bit about the performance of the thing and the status of the project. So far, pretty easy. OK, so what's the purpose of SoftUpdates? The issue is really keeping the metadata of the file system consistent. And there are many different ways of doing it. And this is true not just of FFS. It's true of any file system. And the real issue is, when I talk about keeping metadata consistent, is to say that after a crash or a power failure or some other sort of operation, we have a way of deterministically getting the file system back in a state where it can continue to operate. Unlike pretty much any other development that goes on in the kernel or in user utilities, where crashing and burning and going down in flames is considered OK, it's one area where it is not OK to come up and say that your disk is curdled and you need to restore from your possibly non-existent backup tapes. And so as a file system developer, you have to be much more conservative in what you do, because your users really don't give you the opportunity to fail more than about once. And if you look at RiserFS, it has this reputation for curdling file systems. Well, yes, for a period of time, it curdled file systems. But it hasn't really curdled file systems for the last decade. But it has this reputation, and it seems unable to throw it off so people won't use it. I don't want to get into that category, nor do I really want to go through all of the legal issues that that gentleman went through. OK, so getting back to the topic at hand, what are the various ways of keeping it consistent? Well, historically, the way we did it was synchronous writes. The idea is that if things have to happen in a certain order, then you just do synchronous writes to the disk. And as long as let's say you're removing a directory, you have to remove the directory name, and you write out the zeroed out directory entry. And then the next step after that is you have to zero out the inode. And so you do that synchronously, and then you put the blocks back on the free list. And the drawback to this is that anything that's create or delete intensive since each create or delete requires 2 synchronous writes, runs really slowly. A good, pretty speedy disk, ATA consumer disk, not some huge RAID array, is going to do on the order of a couple hundred I/O operations per second. And so if you're doing something like in a create or delete intensive thing, you're going to get 100 files a second, and that just doesn't really cut it when you're trying to dump 50,000 files into a file system. Brings new meaning to same-day service. At any rate, the next sort of way, the step along the way, is to say, well, let's do non-volatile RAM. So we'll put non-volatile RAM on the machine, and then we'll just put any operations that have to be done to disk in the NVRAM, so if a system crashes, when we come back up, they'll still be sitting there, and we can walk through and deal with them. The drawback to this is, first of all, it's expensive hardware. It is not the most reliable hardware in the sense that you normally have to have a battery, and the battery tends to fail after about 2 to 2.5 years, and the disk typically fails after 3. And so about the time the disk fails, the battery's gone and it's not an NVRAM. And the other problem, of course, is that most machines just don't have NVRAM on it. And so it's a nice idea. And in fact, in things like file servers, it's used to very good effect. But in commodity hardware, your desk-side machines or your laptops or your iPods or whatever, iPads, then it's a non-starter. Okay, next on our list is atomic updates, sometimes called journaling and sometimes called logging. Really, the difference is that journaling is where all we are doing is tracking the metadata, and logging is where we're actually tracking all of the metadata and everything that you write. So something like gjournal, I guess it should have been called glogging under this nomenclature, but gjournal is just tracking every write that happens. And so when we do a rollback afterwards, we in fact recover all of the data that you were writing as well as the structure of the file system. Pretty much everything else here is only tracking the metadata. Now, journaling is the most commonly used thing if you look at sort of most of the commercial file systems out there, things like ext3 and so on. Pretty much all do journaling. And the benefits are that things like create and delete don't slow down under heavy load. And you have a fairly quick recovery after crash because you just go through and roll back the log. The drawback is that you generate extra I/O. Everything, all the metadata at least, is being written twice, once to the journal and once to where it actually goes. And so if you're on a system that is constrained by I/O, journaling is going to slow you down because you've got extra stuff to write. Also, you don't get much speed up for light loads. This is really more of a latency issue. If what you need is really fast, single-threaded operations, then the journaling is not going to be as helpful to you as some of the other solutions would be. But for most people, that's not really much of an issue. OK, next on the hit parade here is CopyOnWrite file systems. The UFS and most other file systems of its vintage are all what we call overwriting file systems. So if you add data to an inode, we simply go and read in the inode off the disk and update the block pointers and the size and whatever else. And then we write that back on top of what was there before. And so what was there previously is just lost. Now, with a non-overwriting file system, you never overwrite any existing data in the file system. So if I need to add a block to an inode, I bring in the inode, I update the information, and now I put it someplace else. And that wouldn't work within the UFS structure because, of course, we have all the inodes in a fixed location. With any kind of a non-overwriting file system, the inodes move around, so you have to have an inode type file which tells you, given an inode number, what block is it on somewhere out on the disk. And of course, that has to also be updated. And often, if you've created a file, then that creates a new entry in a directory, and so things trickle up the tree. So the upshot is, with a non-overwriting file system, what you generally do is you accumulate a lot of changes, and then you periodically write out a checkpoint. And a checkpoint is you write out all the stuff that's changed, usually in a big chunk somewhere on the disk in a nice contiguous area. And then the very last thing you do is you update the equivalent of the super block, what in ZFS is called the uber block. And in fact, in ZFS, the uber block lives in one of 128 different locations. So even that is not overwritten for a long period of time. In part, that's in order to make it work better with flash memory, where you don't want to keep writing on the same thing over and over. Okay, at any rate, the benefits of this is that you get really good write throughput because all the modifications, directory, inode, blocks, all that, chunk, goes down in one place. So you're not, as you are with UFS, writing the inode here and the directory entry there and the block over there. Nice big chunky bits. You're depending a lot on your read cache to give you good read performance because you've got temporal locality. Everything that was written during a particular period gets put in one place. So if you have like a slowly growing log, it's going to have a block here and here and here and here and here and here. And if you now want to grep through that log, you're going to have to seek all over the disk to do that. So the first time you do that, it'll be slow. After that, if you're going to do it with any regularity, hopefully it stays in cache. Okay. Another benefit of CopyOnWrite file system is that snapshots are really inexpensive because all you really do is you just save a copy of the uber block of the file system at the time of the snapshot. So to create a snapshot, you do one of these synchronization operations, which you do with great regularity anyway, and then you grab a copy of that uber block so it doesn't go away, and then if anything gets freed out of it, there's just sort of a linked list of the blocks that are associated with that snapshot. So when the snapshot goes away, you just free that list of blocks, and boom, you're done. So cost of a snapshot is really just the cost of doing one of those synchronizations and a little bit of extra stuff. And so you can make them quickly and easily, and then once you've made it, you never have to worry about like an inode or something being overwritten like you do in UFS, where we're constantly checking to say, oh, are you overwriting something that's part of a snapshot? Oh, we have to make a copy of that. None of that. It's just like, it's right there. We never overwrite anything, so we're just done. And you just keep a long linked list of these uber blocks, and that's really the only, that and the list of blocks that are associated with it. That's all the information that you need. And again, it's just, you want 1,000 of them? Great. You want 2,000? Sure, have a good life. You make 2,000 in UFS, you could like change one file and then go out and have lunch and come back before it would be done checking whether anything was going to be changed. So UFS really, it takes a long time to make them. There's a lot of overhead in maintaining them. And you really, there's a limit of 20, which is scratch defined, but you really don't want to make that a bigger number. Okay. One thing that's not as well understood about CopyOnWrite file system is that they still need to have a journal. And you said, but it's always consistent. Why do you need a journal? The answer is because of this pesky system called Fsck. Fsck says, of course, this file has to be consistent on disk before you return from the system call. Well, one way of implementing Fsck is to take a snapshot, another checkpoint of the file system. But if you take a checkpoint of the file system, every time somebody does an Fsck, you're going to get hosed. You're just going to get clobbered. Because that is not inexpensive. You're not going to write inodes, and you've got to write a bunch of other metadata and directory hierarchies and the uber block and all this stuff. And essentially everything that's dirty in the file system, just because somebody wants one block Fsck, is not an acceptable solution. So the fact of the matter is that ZFS and others like it still carry a journal, and the journal is tracking essentially the metadata changes that have happened because they don't want to lose the data since the last checkpoint, which can potentially be a fairly long time, but mostly to make Fsck work, so that when you do an Fsck, we make sure that your file and all of its relevant data is in the journal, and then we know that we'll be able to recover it. Okay, drawbacks, disk fragmentation because of the way things are written, and memory overhead. Any of you that have used ZFS, I don't have to tell you about memory overhead. Okay. Enter SoftUpdates. Well, the idea of SoftUpdates is that we want to make sure that the disk state is always consistent, as we do with things like the ZFS type file systems. And the way we do this is we keep track of all the things in memory that have changed and their relationships to each other. And we don't want to affect the order in which blocks get written out. So one of the design criterion was we wanted to always allow the VM system or whoever to say, I want that block written and I want it written now. And you're not allowed to allocate any memory to do that. Just get it written. And we can do that, but what we may have to do is we lock it, and then there's a few things in there that we're not ready to let hit the disk yet. There's an inode that's going to be freed, but its directory entry still points to it on the disk, so we can't really let it be freed on disk. So we sort of put it back to the way it was allocated. We let that write occur, and then when it comes back in, we just mark it as dirty again and flip it back and then unlock it. So if someone is trying to access the file, they never really see that we did that rollback because it's been locked the whole time that the rollback happened. The I/O completed, we pushed things back to the way it looked before. And so we never end up with circular dependencies because if two different blocks depend on each other, we can do a rollback on one or the other, and then the other one can be written safely. OK, I'm going to actually go through a little example to show you how it works. The benefits are that most operations run at memory speed because all we do is we sort of update the indoor data structures for the file system, and we create these little dependency structures, and then we say, OK, it's done. And as long as you don't come along and do an Fsck on us, everything's cool. If you do the Fsck, then we actually have to walk the dependency structure and push those things out. But in fact, we only push out the exact set of things that need to be pushed out, unlike ZFS that would have to do a checkpoint or have the journal. OK, the other thing is that the disk is always consistent at all times. And the problem is that it may be behind. It usually is behind the in-core state. So after a crash, you will have lost potentially up to the last 2 minutes of things that changed, unless you've done Fscks. But the fact of the matter is that the disk is consistent. And so you don't have to run anything. You can just go and crash again and go and crash and go and crash and go. As you'll see, there are other things that, where you eventually want to run something because what you end up doing is losing resources, and you want to reclaim those. So the drawbacks are complex code. This is actually something that I put in a long time ago because it was the most complex piece of code I'd ever written, which was 6,000 lines of all these dependencies. And Jeff was reviewing these slides with me. He goes, what do you mean that's complex code? Journaling's worse than that. And I said, oh, come on. Journaling can't possibly be worse than that. And so we pulled up, admittedly a bad example, but XFS and looked at their journaling code. And the journaling code in XFS is 20,000 lines of code. So now I don't feel so bad. In fact, I might even take OK. We have the issue of BackgroundFSK, which does clean stuff up. We'll talk about that. We do get increased memory loading. And it's not as increased memory loading as something like ZFS. When we first did it, we said, well, you need somewhere on the order of 1/4 to 1/2 gigabyte of memory, essentially, to make this run well, where the savings that you get by reduced I/O starts to pay off. At the time we did it, which was a decade ago, that was a lot of memory. Today, people sort of look at you like, what? What's the problem? OK, so this is just a little one example. The thing about SoftUpdates is not that any sort of particular piece of it is complex. There's just a lot of it because there's a huge number of cases you have to deal with. So let's sort of walk through removing a file. So the ordering constraints are that the name that's in the directory that points to the inode has to be gone first. You don't want to have a name in a directory that points at something that's unallocated. OK, so the first write that has to happen is the write that gets rid of the directory entry. And then once you've done that, then you need to zero out the inode and write the zeroed out inode onto disk. And then, and only after the zeroed out inode is on disk, then you can release the blocks and the inode to the free space. Because the problem is if you release the blocks before that time, they could be allocated by some other file, reused, and written out. And then you could end up with 2 inodes on disk that both point to the same blocks. And this is not deterministically fixable. Somebody actually has to look at it and figure out which file each block belongs to. Don't want to go there. OK, so historically, the way we did it was 2 synchronous writes. We deleted the entry in the directory, wrote it out. Then we zeroed the inode, wrote it out. Then we put the blocks onto the free list. Done. So what do we do now? Well, we zero out the directory entry in the kernel buffer. And so we bring in a buffer that's got the directory stuff in it. We go through, we find the entry, we point over it or zero the inode, whatever we're going to do. And then that's now a buffer that needs to be written back at some point in the future. But we just do a delayed write on it. We say, yeah, when you get around to it, write it out. But we hang off at this little dependency that says, by the way, when you ever decide to do this, just let me know that you've done it. And now time passes, typically on the order of 30 seconds or so. And eventually, the buff daemon or this or that decides to write out that particular buffer, and it gets written out. And now when that I/O completes, it notices that there's this dependency, and it calls back into the SoftUpdate system and says, OK, you wanted to be notified when this happened. All right, this block has been written. We go, great. OK, now it's time to deal with the inode. And so when we get that notification, we copy all the block information out of the inode into one of our little dependency structures. We zero out the inode, again, by bringing in the block that's got the inodes in it. We zero it out in that buffer. We mark it dirty and say, all right, write it out, and put our little dependency structure on it and say, let us know when it happens. More time passes, 30 or so seconds typically. And now the I/O eventually happens, and we get notified that, in fact, the zeroed inode is on disk. And we go, great. And we have the little dependency structure with the list of all the blocks that were formerly in the inode, and we drop them into the bitmap. And at that point, we're done. We mark the bitmap as dirty, and eventually the bitmap is going to be written. The place we get in trouble is that that bitmap might not make it to disk before a system crash. And if it doesn't make it to disk before a system crash, then that update of the free blocks is lost. And now when we reboot, it's safe to run because we have a bitmap that claims some blocks are being used that in fact are not being used. But that's not going to cause us any harm. We're not going to double allocate or anything bad like that. But if we do this enough, and because of the fact that these things can go for 30 seconds or so, you can delete a lot of files in 30 seconds. So 50,000 files worth of blocks might be lost. And you do that 50, 60 times, it starts to add up to real memory or real block counts. So eventually, we're going to want to somehow recover those things. Similarly, we might have inodes that we need to recover. For example, we get rid of the directory entry, but we haven't gotten around to doing this step yet. And now we have an unreferenced inode. We need to find that inode, clear it out, get rid of its blocks, et cetera. OK, so the disk state is always valid. The only inconsistency is that we have blocks marked as being in use that are actually free, and we have inodes marked in use that are free. So it's safe to run immediately after a crash, even though at some point we need to recover that lost space. And the way that we had traditionally recovered the lost space was you either took the system offline and ran FSCK, which could take a long time. So we developed BackgroundFSK, which just takes a snapshot and then runs over the snapshot and finds the stuff. And there's a set of system calls that lets it, under the normal operating locks, put those things back in the bitmaps. And the amount of time it takes to run really doesn't matter because nothing bad is going to happen. It's just that eventually some resources show up. OK, well, that worked well for a decade or so. But the problem is now that file systems are getting so huge that the running time for FSCK is measured in many hours. And the load that FSCK is putting on the system, particularly on the I/O subsystem, is substantial while it's doing that. And it makes the whole system slow down. And if it could sort of be run at 1 o'clock in the morning when people weren't doing much on the system, that was one thing. But if it's going to take 24 hours to run, it's going to be part of the midday crunch. And people are objecting to that reasonably. So hence, we enter the idea of saying, well, look, what is the issue we're trying to deal with here? If we simply journal those blocks and we journal the inodes, then we can just do a journal rollback to put those things back in the map instead of having to run this BackgroundFSK. Unlike regular journaling, which requires a huge journal potentially with really large entries in it, because we're only dealing with a very small number of things, events, we don't need a very big journal. I had originally said we needed a 16 megabyte journal, and Jeff objected to this. He goes, 16 megabytes, you only need that on really huge file systems, because it's pretty much independent of the size of the file system. What it really is dependent on is sort of how fast your file system runs, how much stuff it can get done. 16 megabytes, since each entry is only 32 bytes, you can get a lot of 32-byte entries into 16 megabytes. And so you can, with tunefs, artificially push that down, I think, as small as 1 megabyte. And the main reason that Jeff did that was so that we could test what happens when they run out of journal space, because you need to essentially be able to handle that. And even with it only at 1 megabyte, running on a 1 terabyte file system and just doing all we could to try and make trouble, it was difficult to run out a 1 megabyte journal. Okay, so what do we actually need to journal? Well, one of them is an increased link count. So with increased link count, the issue is you've, let's say, done a hard link to a file. And so what happens is you increment the inode, or the link count on the inode. And then once you know that the inode with the increased link count is on disk, then you're allowed to create the directory entry that points to it. And of course, this is just, or creating a new file is a special case of this, where it's going from 0 to 1 and you're creating the first entry that points at it. So if you have managed to get the link count bumped on disk, but you haven't managed to create the new directory entry, then what BackgroundFSK or the journal needs to do is recognize that and decrement that link count on that inode so that it properly reflects the number of names that actually point to it. And so one of the things we need to journal is anytime we increase a link count. And what's causing the link count to increase. So we say this inode is getting an increased link count because of this directory entry that's being created. And later when we go to clean it up, what we're going to do is we're going to say, OK, did the increased link count happen? Yes. Does that entry exist? No. OK, decrement this. Or it does exist, so therefore it's fine. OK, decreased link count, more or less the same story. We need to delete an entry first, and then we decrement the link count. That's what the case we just looked at. So again, we need something that says this link count needs to be decremented if this directory entry doesn't exist. So the rollback is check if it exists, and if it exists, then leave it alone. And if it doesn't exist, then decrement the link count if it hasn't happened already. One of the nastier ones, and this is actually something that gjournal has a bit of trouble with as well, is the notorious unlinked files. So if you open a file and you continue to hold a file descriptor to it, but you then delete the name of that file. So let's say you create a temp file, you open it, and now you delete the name. And the idea is when you close that descriptor, possibly days later, the reference count on it will go to 0, and at that point we reclaim the file. Well, we have the link count hasn't changed, but there is no name for it. So we need to the reference count has changed. So we need to have a list of those inodes somewhere, because again, what we would have historically done with the BackgroundFSK is we would have found these inodes that were no longer being referenced, and we would reclaim them. But we need to know where they are. And this turns out to be one of the nastier problems, because we actually have to keep a linked list of them. So there's a field in the inode headed by a pointer in the super block, which points to the first one, and then there's a whole long list of them. Cleanup is easy. You just run down the list and get rid of them. But actually trying to keep track of whether a linked list in memory is consistent turns out to be, or on disk is consistent, turns out to be a real issue. I mean, you'd say, well, you're just adding things onto the end of the list, but that's not true, because when one of these files gets closed, you have to take that file off the linked list and make sure the previous one now points to the next one, and all that stuff has happened on disk before you allow certain operations to occur, et cetera, all while keeping track of the fact that this is going on in the journal. This turned out to be one of the hardest things that we did. Change of directory offset, another wonderful little problem with UFS. If we're going to go create a new entry in a directory, we might have a couple of spaces that aren't big enough of and by themselves. So we just go and compress everything down, and then we get one big chunk of space, and we put the new directory entry there. But what that means is that the offset of a bunch of other entries in that directory have now changed. Go back to what I was talking about here. We say, oh, the link count has increased, and the directory entry that points to it is, oh, right there. Except that right there is now actually over here, because somebody did a compaction in the meantime. So another one of the things that we have to keep track of when we say a directory entry is at this offset is also every other offset that it's been known to live at. And so into the journal has to go any directory that we're tracking and gets moved due to a directory compaction, we also have to know that that happened. OK, and then finally, the thing that we started out, which we thought was the hard part, is the updates of the cylinder group to reflect the new blocks going in there. and the freed or allocated inodes happening. And so we need stuff so that we can make sure that this also gets dealt with. Okay, so you're beginning to see that when you actually start to dig down into this problem, which look like how hard can it be, well, you'll see the statistics at the end, but it's not as trivial as was originally thought. Let's just say that Jeff went to the FreeBSD Foundation and said, oh, I want to do this, and it's not, it's only going to cost this much money. And well, he ran through that money, and so then he went to Juniper and said, well, it's only going to be about this much more money, and he ran through that and went to a third organization and got some money from them, and he still put in a lot of free time, and I was giving a little bits of help along the way as well. So it really exploded into a much bigger problem than either of us had any idea. In fact, if we'd known how hard it was going to be, it probably wouldn't have happened. But that's the beauty of youth and enthusiasm. Okay. So what this means is that we need to add new dependency structures. So there's dependency structures that are in there for deletion and addition of directory entries and deletion and addition of inodes and so on. Some additional stuff that we need to add is things to keep track of cylinder group rollbacks. It used to be that we could write a cylinder group anytime we wanted, and we never had to do any kind of a rollback on it, because the only things that we were ever updating on it were these free blocks. Well, we would allocate blocks, but that would always be written before anything would claim them. So if it didn't happen, it didn't matter. In the case here where we're writing them out to free them, we need to make sure that there's a journal entry reflecting that before we allow the actual thing to get written, so that we can make sure that we're going to be able to get things set up properly after a crash. There's also already a number of places where we need to do rollbacks of inodes. There's additional rollbacks of inodes, again, having to do with whether the cylinder group properly reflects its allocation or not. All right, another problem or issue is that we've got this journal, and it's just a circular log. We just keep plopping new stuff at the end, and as things get dealt with, we need to sort of remove them from the end. And the question is, where is the end? Where's the last valid thing that's in this journal? Sort of how far can we go before we run into it? And so every dependency that we have that has something to do with a journal has a pointer to where in the journal its thing depends. And it's not the actual location of the 32-byte thing. It's actually a pointer to the beginning of a block of those things, because we write them out in chunks. And so we can then essentially, by tracking sort of what's the oldest one that has a reference to it, we sort of know where the back end is. And so it turns out if we're beginning to run out of journal space, it doesn't do us any good to get rid of stuff in the middle of the journal, because the tail has to move forward in order to get any new space. So we concentrate on getting rid of stuff that's going to free up entries that are old in the journal, because that's the thing that's going to help the problem at hand. Okay, and as I said, things are aggregated into segments. There's a paper which I'll give you a reference to. So if you actually care about this stuff, you can go read the details. But when all the dependencies within a segment have been dealt with, we can then release that segment. Okay, and I've already sort of alluded to the unlinked inode list. This is the list that's headed by a pointer in the superblock. That is all of the inodes that are unlinked, but still actively being referenced. Because then after crash, of course, they've got to go away. All right, so that's the stuff that we need to journal. And now the question is, how do we go about doing crash recovery? Well, crash recovery is done by the program that you've all come to know and love, FSCK, because the last thing that you want to do is to try and have to teach administrators or anybody that writes scripts how to do something new. And it's easy to just say, well, just run FSCK. And FSCK looks at it and says, oh, there's a journal here, and then does a journal rollback. And then if that fails, it can fall back to doing it the hard old way. So from the user's perspective, you just run FSCK, and the right thing happens. Now, part of our thinking was, oh, we're going to be able to reuse big chunks of FSCK. No, turns out almost every line of code for a journal rollback is new code. Another one of those ones where it took a little more time than expected. Now, one of the benefits of this journaling system is that the recovery is idempotent. And the reason I can say it's idempotent is because we just say, well, memory is not a problem. And with FSCK, FSCK has always been a memory hog. So even though the thing I'm about to describe to you uses a ridiculous amount of memory, well, actually not that ridiculous, it's far less ridiculous than what even background FSCK would use. So I don't feel too bad about it. So here's the way we do it. We start by reading the entire 16 megabyte log into memory. That's 16 megabytes, we're just getting started. Okay, so 16 megabytes, we just read the entire thing into memory. Now, once it's in memory, we search around, we find out where the head and the tail is. And then, remember I said we were keeping link count increases and decreases? Well, we don't want to go through and some particular file has had lots of increases and decreases during the period of time of the journal. So we just walk through and we match them all up. And so for every increase, we find its corresponding decrease, and they disappear in a cloud of greasy smoke. And we get it down to saying, OK, when all this dust settles, what we actually needed to do was nothing. Or this needed an increase by 1 based on that name or whatever it was. And so we start essentially by compressing the log down to sort of the minimum set of things that need to be done. OK, once we've got that, we then start, let's say we have an inode and we need to change a link count. So we allocate the 16K block for that inode. We read that inode block in. We decrement that count. We do not write it back. We just keep it. And we just get all the buffers of every block on the file system that needs to be changed in memory. And sort of the worst case scenario that we have here is that each 32-byte entry in the journal requires modification of a different 16K block. And even with that, and if we're running a 16 megabyte journal and it's completely full, we're still only using 2 gigabytes. So it's not that bad. And you've got to really work at it to make it be that bad. The real purpose for this is we're doing all these various integrity checks and other checks to make sure that things are absolutely consistent. And once we process the entire journal and we have the entire set of changes and we haven't found any, we haven't tripped any asserts and everything looks absolutely correct, we say, cool. And then we just write all those blocks out to the file system and we're done. And the final point is that it's idempotent because even if we're partway through writing out those blocks to the file system, and then the system crashes unceremoniously right there, we can run it again and go through the log, and it will figure out the same set of things, except half of the things we will found have been done. The other half haven't. So we build up that set of blocks, and we try and write those out. And that crashes, but we keep banging it down and banging it down and banging it down until we finally get those things written. Once we have consistently gotten all those blocks written out, we then go mark the journal and say, this is done. We mark the file system and say, it's been done, and we're now ready to roll. And during the Dev Summit, somebody had turned it on and tried using it and deliberately crashed their machine. And they said, well, it came up and FSCK flashed something about a journal, and then it was just booted. Was that OK? And it's like, that's the point. OK, so the steps to be a little more precise here, we're going to start by scanning the journal, bring it all into memory. We then compress it down to get the minimum set of changes. For all the link count increases, we go and we check and see whether the directory entry got created that corresponded to that increase. If it's there, there's nothing to do. If it's not there, we need to get rid of that increase. Similarly, for decreases, we look to make sure that the thing that went away really went away. And if it did, we do the decrease. Any inodes that after we've adjusted the link counts now have a 0 link count have to be freed. And again, this is the whole process of, you don't just free the inode because it probably claims blocks, so you got to walk through and free all the blocks that are associated with that. We walk the list of the unlinked inodes and do the same thing where we have to free up all the corresponding resources that are with them. And then finally, the journal has some blocks that needed to be freed, a bunch of blocks that got freed as a result of these inodes. All that needs to be written out. And again, when I talk about writing this stuff out, we're bringing the cylinder group maps in and updating them appropriately and just holding them in memory until everything is done. Everything is, we don't have something where, one of these things somehow points to something that shouldn't happen, or things that are supposed to be blocks aren't blocks, or whatever. And once everything looks cool, all those cylinder group maps get written, and all the inode blocks get written, directory entries get written, etc. Okay, so that's the crux of crash recovery. So how well does it actually do? Well, the proof is in the pudding. It's not going to make things run faster. It's never going to be faster than regular soft updates without journaling because, well, we're doing extra journaling that we weren't doing before. And so the best you can hope for is that it doesn't get worse. So we better get something for our money here, and what we're getting for our money, hopefully, is better recovery times. So there's sort of two things that we sort of did as examples. One is an 8-way build world on a 250 gigabyte, 80% full disk. And when we say reset after 10 minutes, this is with extreme prejudice where we power fail it. And so the journal recovery in that case took 0.9 seconds. We then, while we're doing all of our testing, always would run a verification FSCK because after the journal is done, FSCK had better not show anything wrong. I mean, even the super block summaries had better be correct because even one of those is wrong, we're missing something. So we would run the FSCK verification, and that would take another 27 minutes. The other one was a random collection of parallel file writes on an 11 terabyte, 92% full 14-disk 3-ware RAID controller reset after we had several hundred megabytes of data sitting around in various states of getting written to the disk. And the journal recovery here was under a minute. It's on the order of about 50 seconds. The verification FSCK took another 10 hours. Okay, so what's the runtime slowdown? We have additional I/O that's going to the journal that we didn't have before. The journal is small, and the amount of data that's actually going there is really not that much. To try and get an idea, essentially, of what it was, how much it was slowdown it was causing us, we did a test where we went into the code and got through the code to the point where it was about to actually write to the journal, but just truncated that so it didn't actually do the I/O. Just to sort of see what the effect was going to be of, we didn't actually do the extra I/O. And this, of course, is onto the same disk where all your other I/O is going. We couldn't measure a difference in performance. So it's obviously not that horrendous. The other place, though, that is noticeable is where previously you would be able to proceed, and now you block because we need to have a journal write before we can let you proceed. Now, in a lot of cases, this doesn't really matter because it's all happening in background like we're removing a file. So the fact that it takes a little extra time for the file remove to happen isn't really that big of a deal. But there are places where it does show up, and this is when you're writing large files, and we, for whatever reason, have to stop and write something to the journal about a cylinder group, and that, the cylinder group can't be changed while that's happening or whatever. This, in fact, is one of the performance things that Jeff is working at right now, because it is noticeable, and we're hoping to, we have some ideas on how to fix it, but we haven't got there yet. And then there was concern, especially on Jeff's part, of all the extra CPU overhead of doing this. And I said, Jeff, look, don't worry about it. Now, compared to I/O, CPU is free. And he didn't believe me, but now he does. You just, the running time of things is not measurable, the additional running time. Okay, so let's talk a little bit about the status. It's been merged into the head of the tree. This happened about 3 weeks ago. There were a flurry of bugs that got reported. In fact, the tunefs was the one that had the biggest problems because it was being updated, but then the update of the super block wasn't happening quite right, and sort of bad things happened. At any rate, the known bugs have been fixed, although just as Jeff was leaving, he said, oh, someone reported another bug, and I haven't found it yet. So I'm not allowed to say all known bugs are fixed, but the known bugs at the time I wrote these slides are fixed. The performance work is in progress. The issue is to clean up some of these things where you're blocking to write the journal to try and mitigate those. Jeff has actually done ports to 6 stable, 7 stable, and 8 stable. If you want to try one of those, it's in project/suj/6, 7, or 8. They are not absolutely up to date, and there's no intent of MFCing them. This is much too big of a change. But if you want to try it out and you're in an environment where you don't want to be running current for some reason that I couldn't imagine, you're welcome to try those. But if you're going to report bugs, reporting against that, you may well be reporting something that's actually been fixed in head. So if one of those is of particular interest to you, you can talk to Jeff, and maybe he'll be nice and update it. OK, another one of the goals in all of this is to make it really easy for people to try it out. And the way you make it really easy for people to try it out is that you can turn it on, and if you don't like it, you can turn it off again. And in particular, one of my requirements that Jeff was somewhat resistant to was that soft updates with journaling had to continue to work. He originally wanted to just say, soft updates just always has journaling, end of story. There are times where you don't want that. You want soft updates, but you don't want the journaling part of it, especially in something like an embedded system where you need a particularly small footprint. In fact, in that case, you may not want soft updates at all. But it's more overhead, more memory, et cetera. And so I insisted that it both be possible, and they are. So the way you enable it is you run tunefs. There has to be a minimum of 16 megabytes of space available to create the journal. If your file system doesn't have 16 megabytes of space left on it, you've got bigger problems than soft updates. At any rate, another one of the issues is what happens when you boot old kernels. You might have a current kernel that you want to test this on, but then you're going to go back and run your stable kernel when you put the thing back into real use. And so we want to be able to know that this sort of thing has happened. And so if we have a system where the journal, we've been running with journaling, and you boot an old non-journaling aware kernel, it will see that the dirty bit is set on the file system. So it will know that it has to run Fsck before it can mark it clean. And the other thing is that we want to know that an old kernel has been run on there, and that the journal, even though it's there and may look like it should be used to roll back the file system, in fact, you don't want to get anywhere near that journal. So one of the things that I did eons ago when I first did UFS2 was I added a flag that the kernel always cleared every time you mounted it. My idea for that flag originally was that we were going to have B-tree indexes on the directories, and so I wanted to know that some non-B-tree aware kernel had run, and so I might need to update the B-trees before I used them. So that flag was there and was being cleared. We just co-opted that flag to say it's the using soft updates with journaling. So anytime you run an old kernel on your file system, it's going to clear that flag, and now if you run a journaling kernel, it'll see that it's been turned off, and it'll know that the journal is crap and should be ignored. And also that it needs to run regular Fsck if the file system is dirty. OK, so it's fairly safe to move back and forth between different kinds of kernels with and without soft update journaling. You can turn it on with tunefs. The one place where it gets a little bit problematic is that tunefs normally has to run on an unmounted file system. And that'll work on everything, of course, except for your root file system. And so tunefs and other programs that want to operate on the root know that if root is in read-only mode, then it can go out and make changes, like the background, or Fsck can run on the root file system, and then it does a reload file system to pull in anything that's gotten changed. And so we can do the same thing with tunefs, where we create the journal and then reload the file system for the root. Now, this, it turns out, only works on the root when you have first booted it up. As soon as you make it read-write, even though you can downgrade it to read-only, there is an anti-foot shooting provision that got put into geom that says once it's ever been writable, don't ever let anybody open it again for writing. And so you can't downgrade it to read-only and then tunefs it. I view this as a bug, and that we should allow that to happen. And there was lots of gnashing of teeth about people shooting themselves in the foot. And I keep explaining that we're vendors of rope, and you're supposed to know how to use the rope. And if it ends up like this, it's not our fault. OK, so interesting statistics. 11 new dependencies were added to the existing 14. So we originally had 14 dependencies. There's 11 new ones that got added for journaling. I'm sure you're desperate to know what they all are, and you can read the paper. They are all explained in the paper. If you make it all the way to the end of the paper, send me a piece of email. Okay, it nearly doubled the size of the SoftUpdates code. We went from 6,500 lines of code to 11,500 lines of code. And in addition to that, the journal recovery code is another 2,600 lines of code that goes into FSCK, which nearly double the 6,000 that were already there. That was almost 50% more. So it was not a small project by any way, shape, or form. Part of the business with FSCK is we really thought we could share a lot of the FSCK code, and you just can't for a number of reasons. Adding the new dependencies was actually pretty easy. I mean, the structure in there for doing dependencies all works pretty well. The thing that was actually more difficult was figuring out what all the new rollbacks needed to be and getting that stuff coded in. And for whatever reason, that just turns out to be the part that's harder. The dependencies are sort of obvious. It's like, well, this depends on that, and so we need a dependency structure for it. But then it's like, well, now, if take the case of the linked list that we needed for the list of unlinked. Think about the dependency structures and what has to happen in what order when you're removing something from the middle of a list. It boggles the mind. Okay, it turns out that my old friend directory rename consumed about a quarter of the development time of SoftUpdates. Now, back in 1982, I did my first implementation of rename. And I was told at the time by Dennis Ritchie that this was going to likely be difficult, and I should think about whether I really wanted to allow rename of directories from one place to another. I, being about Jeff's age at that point, figured, how hard can it be? This is the 7th time I've been involved in rewriting it, and I already know that it's still not entirely correct, because we figured out yet another way that we could get ourselves tied up in knots. But the window's getting smaller and smaller.
How long is directory rename now?
Oh, I'm sure it's not more than 1,000 lines or so, as long as you don't count the peripheral functions that it needs. The thing that actually made it easier to get it closer to correct is the fact that we now have recursive locks. We didn't used to have recursive locks, so we had to lock the first thing, lock the thing we were going to move. Then we had to unlock that while we locked the destination. And then we had to go back and relock this. And then things could have changed back here, but we might not have quite realized it. And now we can just lock this and lock that. And there are various ways that you might get yourself into a deadlock. So we actually do try locks all the way down. And any time a try lock fails, we wait till that lock is available and then unlock everything we have and start over from the top. It's not really pretty code. But it seems to work better than it used to. OK, I've given up saying we've got the rename problem solved forever. It's like.
When's number 8 coming?
When's try number 8? I'll get back to you on that one. OK, so there's a paper that we've written. Jeff and I actually went through it, and we have a whole bunch of changes that we're making to it. And Jeff's like, oh, I'll have those done for you, by the time you give your talk on Friday afternoon. I said, Jeff, you're about to take the flight from hell back to Maui. Somehow I just don't see this happening the morning after you wake up. And he hasn't sent me any email yet, as far as I know, saying it's updated. So, but the paper's there. What's there is correct. It's just some parts of it are a little skeletal, like it's one sentence that needs to be about a page. But you'll get the general gist of what's going on. The slides that I just did are at that second point, and they'll be on whatever the server is here afterwards. My email address, I'm McKusick @ but I'm not as good at reading my FreeBSD.org mail as I should be. I'm better at reading my McKusick @ McKusick.com email. So if it's something that you want a response within, say, a month, I recommend that you use this address. Similarly, Jeff has a Jeff @ and also this one. From my experience, he tends to be more responsive to this address. I will say about Jeff that you either will get a response nearly instantly or not at all. Unlike me, he doesn't have factor in a 1-week delay and then answer stuff. I think he just deletes any mail that's more than 24 hours old on the grounds that it's not interesting anymore. It's not relevant. If it's important, they will have sent me the update. The rate at which he actually codes, that's probably true. You know, I mean, if it was a problem 24 hours ago, it's probably been fixed by now, so, you know, don't worry about it. You know. So I always read my mail from Jeff backwards, you know, from the most recent ones working back, and that seems to be a good algorithm to use. Okay, so with that, I will take any questions that people have.
So would there be any point in putting the logs on some other media, like Fsck or?
If you had something like NVRAM or you know, some other sort of faster media, that would certainly help you, because that would get rid of all the places where we block on the log. That would be a simple solution to the performance issues that we're seeing. Putting it on another disk probably wouldn't make much difference, because we haven't found that to really be a bottleneck at all. Someone said, well, why don't you put it in Flash? It is, you know, rotating around through, but it is still being written at a fairly good clip. So I think you would run the risk of you know, running out of your quota of write cycles on the Flash sort of more quickly than you might want. Although we haven't actually studied how fast it rotates in real use, because we run the really nasty tests that are designed to just pound the piss out of it. Yes, Jordan.
So speaking as a vendor who's got quite a bit of knowledge out of journaling alone, as an add-on to an existing file system, what are the benefits that you see?
Doing both of them is pointless, because they're both doing the same thing, so you'll just do a whole lot of work when either one would do, and you're only going to roll back with one or the other. So generally speaking, I don't think you would do that. The benefits of soft updates with journaling is that there's a whole lot less journaling to do with soft updates. And so the extra I/O load that comes from the journaling, there's just a lot less volume, and because the set of things that you need to fix is so constrained, the recovery tends to be quicker. We're running with essentially a 2-minute checkpoint on our journal most of the time. And if you do that with a regular journal, your recovery time is going to be more or less 2 minutes. And so, you know, we, on the other hand, normally, our normal journal recovery is under a second. So, you know, there's that benefit. The drawback to the soft update journaling as opposed to pure soft updates is you cannot, well, you can boot and run immediately on the file system, but if you've done that, now your journal is hosed. And so your only recovery to get back to being able to do journaling is to run a BackgroundFSK at that point. And so and for something like an embedded system where the really fast recovery, where they don't want to do journal rollbacks, they don't want to do anything, they just want to boot and run, they're probably not going to want to use the soft update journaling. They're willing to deal with the resource recovery instead in some way. Okay, any other questions? Yeah, Mike.
You said that you cancel offsetting operations during the journal recovery, but what if
the actual thing that's in there is for each one of those link count changes, it says what the absolute number ought to be. And so once we've aggregated the things in the journal to sort of see what cancels in the journal, we know which one of those absolute numbers is the correct one to be checking for. And so, you know, it may have been fluctuating around based on what's out there. Some may have happened, some may have not. All we really need to know is what's sort of the last one that's relevant to us. And that one tells us what the number is absolutely supposed to be, and then we just check that. Yeah?
You mentioned solid-state disks, and you mentioned the problem with the journal of 16 megabytes.
We haven't done any tests on solid-state disks. One of the things that I mean, Jeff's response is, sure, we should use a flash, because he says flashes are much bigger than 16 megabytes. They're, you know, you can get 4 gigabyte flash, and so we'll just make the journal 4 gigabytes, you know, and it'll run all the way around 4 gigabytes before it comes back around to the beginning. And so, in fact, you know, the rate at which we'll use up the lifetime of the thing will be sufficiently low that the disk will die before the flash does. And that may well be true. We haven't tried like running a FFS type file system on flash because of the fact that certain things like the superblock and cylinder groups get rewritten over and over and over again, and so it just is not well suited to that. Something like a ZFS type file system, which was in part designed to work with flash because of the fact that it's non-overwriting, and even things like the Uber block, which is nominally written in the same place, is actually written, you know, in a bunch of different places to reduce that wear leveling. Yeah. Okay. No, the answer is we don't, because all we're doing is cleaning up the existing file system. We never have, I mean, if we needed to do something like create a lost and found directory or something like that, then yeah, we would. But that's not one of the things that we will ever do in recovery. All we're doing is we're taking the existing allocation, if you will, and just making some cleanups to it. So all we're ever going to really be doing is adjusting some link counts, adjusting some bitmaps, and maybe zeroing out an inode. But that's it. So because of the fact that we're not doing anything that would traditionally cause new files to be created or whatever, we never need to do any additional journaling. Yes?
Can your journal file get corrupted when there's like a power failure and that it might just write crap?
We do checksums, basically, of all the blocks. So when we read them in, we verify the checksum. And Colin will probably have a cow because it's just a checksum, but at least it's a start. Yes?
At this time, is there any point to turning this on file systems that are dedicated?
In general, I don't think so, because the database is pretty much managing that. I mean, the database just thinks it has a raw disk, and it's going to be doing its own journaling and all the rest of it. And, in general, running a database on top of a file system doesn't seem like that wonderful of an idea, but there's people that do seem to want to do that. Okay, well, we are out of time. I'll be happy to answer more questions down in front. Thank you for coming.